In this section, we're going to focus on finding material options for a space frame chassis. The rules do give some guidelines about strength and stiffness, but there are other things to consider, like, for example, how the materials behave when exposed to extreme temperatures. And then there's cost and availability to think about. The material selection methodology by Professor Mike Ashby allows you to do this efficiently and allows you to justify your decision in the competition. For our selection, we need to define the function, the constraints, and the objectives. By function, we mean the geometry and the primary loading condition. Now, in this case, our space frame is made up of hollow tubes. That's our geometry. And for this, we're going to consider the frontal impact load condition. And we've taken this from another innovation course, the space frame chassis analysis using ANSYS Mechanical. In that condition, the front beams receive the highest deformation. And for the purpose of material selection, this is best represented as a beam loaded in bending with fixed supports. The constraints are the non-negotiable criteria. What are the properties the material absolutely must have? Now, the competition rules can place some constraints, for instance, a minimum Young's modulus or yield strength or carbon content. And we can also place constraints in our selection. For instance, a minimum or maximum service temperature and choosing materials that are definitely non-flammable. And then our objectives, what do we want to minimize or maximize? In this case, we are interested in finding the lowest weight and lowest cost materials. And the combination of the function, constraints, and objectives give us the performance indices. In Granta Selector, start by going to Chart and Select and choosing a subset of materials to work with. We're going to go with all bulk materials because that removes things like fibers, which we can't use for this application. We can also exclude ceramics and glasses. They're definitely too brittle. And we can remove magnetic materials. And with this done, click Apply. And we'll be down to just over 3,000 materials for the next data selection. For the next part, we want to place constraints on our selection. For that, we go to Limit. And under Limit, we can find in Composition Detail, Carbon, and set the minimum value of carbon that we want, which is 0.1%. Under Mechanical Properties, we can set the minimum value for Young's modulus, which is 200 gigapascals, and for yield strength, 305 megapascals. We can click Apply here. And we've constrained our selection to just 569 materials, but we're not done yet. We're also interested in looking at how the material behaves in certain thermal environments. So we can set the maximum service temperature to have a minimum of 90 degrees. And for the minimum service temperature, a maximum of -20 degrees. Under durability, we find flammability, and we want to choose materials that are non-flammable. And click Apply again. We reduced our materials a little bit more. Now for the next stage, we're going to use performance indices to optimize our selection. Under the Help function in Granta Selector, you can find lots of information about performance indices for standard applications. For this particular selection, we're going to use a tool called the Performance Index Finder. Go to Chart and Index, and this is where you find the Performance Index Finder. When I click on it, it allows me to choose options. Under Function and Loading, you find the geometry and loading condition that most closely resembles what you're selecting for. In this case, the beam and bending. For free variables, we're choosing the section area, and that means that we can make the section area bigger or smaller based on the design needs or the material properties. And that leaves us with fixed variables of length and section shape. For the limiting constraints, we're going with stiffness because that is the most important mechanical property we want to optimize for our selection. When it comes to objective optimization, here are the options, and we're looking to minimize the cost and the mass. For the y-axis, we'll go with mass. On the x-axis, we'll do exactly the same thing. Performance Index Finder, under Function and Loading, choose Beam and Bending. Free variable, fixed variable, limiting constraint, and in this case, we're going to optimize the cost, which means the lowest cost possible, and then click OK. What we have now is a chart of all the materials that have met our criteria, ranked based on their mass per unit of stiffness and their cost per unit of stiffness. To have a better view, remove the grayed out materials that have failed the selection, and then zoom in. If cost were no objective and we just wanted the lightest material at whatever cost, then these ones over here will be the best ones. Beryllium, well, we can't use that. It's a toxic material. But here we have an aluminium fiber composite. It's low mass, but very high cost. Cost is something we did want to consider. So what we can do is create one more chart that compares all these materials based on their cost. Back to chart and index. On the y-axis, we can look at the price. And if you want to include sustainability considerations in your design, then on the x-axis, you can look at the carbon footprint. And click OK. Once again, remove the materials that have failed the selection. We're going to zoom in. We still have a lot of materials to look at, so we can use the box tool to just zoom in on the very few at the bottom left-hand corner that have the lowest price and lowest carbon footprint and still fulfill the criteria. Let's zoom in. And these are our top candidate materials: carbon steel, structural steel, and several others. And these are the ones that we can choose out of this entire subset. Now, the last thing we want to do is to make sure that the material we choose actually makes sense. You can do this by checking that particular material. How is it typically used? Double click on the name, and it takes you to the data sheet for this carbon steel, the AISI 1095. And under typical uses, you can see that this material is used for general construction, automotive, gears, springs, electric cars, etc. So that seems to me that this is a good choice.